All right, hey, welcome back, guys. Got our second video right here, number 22. So one of the later problems in your asynchronous problem set today. So hopefully this helps out a little bit here. If you're just like feeling a bit overwhelmed, watch this video, get you guys up and running here. So number 22, let me go. I didn't put the prompt on there. I apologize for that, but the prompt is right here. We got a quadrilateral D-E-C-K, deck, I guess. I don't know. D-E-C-K, it's a parallelogram. So they're giving to us that it's a parallelogram. So we're going to know that opposite sides are parallel by definition of parallelogram. We're also going to know that opposite sides are congruent by the theorem. Opposite sides of a parallelogram are congruent. We're going to know that opposite angles are congruent. There's a whole bunch of stuff. The diagonals bisect each other. So KT is going to be congruent to TE. We would know that, right? Just simply by its parallelogram, okay? We use these facts to rattle things off to then prove more interesting things later, right? So you want to be quick at a lot of the theorems that we have here. All right, let's see what we're dealing with. What sort of the theorem we're going to flex today? What definition we'll flex in order to solve a problem like number 22? Let's maybe check this one out. DE equals x plus y. Okay, so I know that I'm going to have this side of this being represented algebraically as x plus y. Again, one of these hybrid algebra geometry problems. EC is 12. And CK is 2x minus y. KD, 3x minus 2y. And then we got to figure out what x equals, what y equals, and the perimeter of the freaking thing right here, okay? So this to me is jumping out to me. This to me looks like it's going to be, especially for those of you who didn't take Algebra 1 yet. I got a couple freshmen. This is going to be a systems problem, okay? A systems problem. What a system of equations is defined as is two or more equations that share the same variable. So here we can set up two equations in this, and they're going to share the same variables. What are the variables? X and y. And what are the equations? Well, we need to set up those equations here, okay? So for instance, one equation I know that I can set up is this. KC's got to equal DE. I can deduce that because opposite sides of a parallelogram congruent to one another, okay? I can also deduce that KD is congruent to C because I have a theorem that says opposite sides of a parallelogram are congruent to one another. So that means the lengths of the sides need to be the same here. So I can set up two equations, one of which is going to be, let's see, KC equals DE. I can set up 2x minus y equaling x plus y, right? I got that from right here, and I got that from right here, which I got from originally earlier in the problem. Lots of stuff to keep track of here in math. KD is 3x minus 2y, and CE is 12. Okay, it's 12 here. So now I got a couple equations. And what makes systems equations harder is look at this left equation. How am I going to figure out what x equals? How am I going to figure out what y equals? I got x and y both problems. How am I going to figure out what x equals? How am I going to figure out what y equals? Okay, so what my recommendation is when you have problems like this, okay, when I have problems like this is do it this way. This is the way I recommend. There are other ways you can do it. If you've studied systems before, you should have like three ways to solve a system. This is from Algebra 1, but if your Algebra 1 teacher hasn't gotten there yet, or it's been a while since review, my recommendation would be is to, one, isolate one variable. Maybe I'll write this down here. Isolate one variable in one equation. Okay? So if I can get, say, y by itself in one equation or x by itself in this one, what that's good for that is I can then substitute, okay, what that variable is equivalent to into the other equation. Now, as a math teacher, as a teacher, it's very hard to give you those steps and to have them make sense without doing an example. So let's do that as an example. Let's cross-check into those examples that I just gave you guys right here. Isolate one variable in one equation. It could be either one. So for instance here, we can think about isolate means get by itself, okay? That means mathematically we want to get it by itself. Okay, so that's what isolate means. Get it by itself. And the way I'm going to do that here is, look, we have x plus y right here. X is almost by itself, right? X is almost by itself right here. Y is almost by itself. So what I'm going to do is I'm going to get x by itself. right? Let's get x by itself. So in order to get x by itself, I can subtract y from this side and subtract y from that side. And here, adding a y, taking away a y makes a 0, right? Makes a 0. As long as I subtract y from one side of the equals and I subtract it from the other sides of the equals, I'm using the subtraction property of equality to keep the equation balanced. So on the left side of the equation, I'm basically rewriting one equation to get one of the variables isolated here. And look, negative y, subtract another y, brings you down to negative 2y. And that's going to equal x. Now I have x isolated, okay? So step one's done right now, right? What is x, okay? So what isolating one variable means x equals question mark, right? X equals question mark. Okay, so what we're going to do is we're going to take what x equals, which is right here. X equals 2x minus 2. That doesn't make sense, right? I don't have the x isolated. Let's see. I'm jumping ahead a little bit here. X isn't isolated because x is on both sides of the equation, right? We don't want that, right? We don't want the x on both sides. We want x by itself on one side of the equation here, okay? So let's back this up. I apologize for this. We're backing it up. Oops, I can't actually erase much else here. I'm going to keep isolating x here. And what I'm actually going to do is I'm going to move the y back. I'm going to move the y back over here because I got to get rid of that x. And I got to get rid of one of these x's here. Oh, man, I might have lost you. Might have lost you right there. That's the reason why we do tons of examples. 2x minus x becomes x. Negative 2y plus 2y, that's going to make a 0. So now I brought my x over here. And I've subtracted my x over there. And I've added 2y, because look, I had the 2y here. So x equals 2y. Okay, now I have my x isolated. X equals freaking 2y. Let's check this out. It equals 2y, okay? It equals 2y. So what we're going to do is we're going to take 2y, and the second thing is we'll take this 2y, and we're going to replace it for x in the other equation, okay? So remember, there's lots to keep track of here. This was our original equation, kc equals de. Now we have kd equals ce right here, but we've gathered some intelligence. We know x can be rewritten as 2y. We proved it over here using the properties of algebra. X equals 2y. So now we can take this x right here, and we can replace it in this equation. And instead of writing 3x minus 2y equals 12, we can do 3x minus 2. Wait, no, not 3x. I don't want to do 3x. I want to replace 3x with 2y. Okay, so we'll take this. Instead of writing 3x, I'm going to do 3 times what x represents, which is 2y. 3 times by 2y. And then I got the minus 2y right here, equal to 12. And look, I'd be able to solve for y right here. Okay, so let's do that up here, right? Let's do that up here. Let's see what we got. And we're going to replace, okay, so remember, we're going to replace the x with 2y. And I'll do that with parentheses because mathematically, we would know what to do afterwards here. When we replace something, put parentheses around it. That means 3 times by whatever x is, then x is 2y. We'll multiply in a second. And now we're going to subtract 2y from it. Oops, let me switch back to black. Hopefully you're following along here. Just double check here. Maybe you rewatch. Maybe you send me a message. Maybe it's 4, and then it makes sense. 3 times 2y is 6y minus 2y equals 12. 6y minus 2y is 4y equals 12. And finally, we've solved for y. Divide both sides by 4. Y is going to equal 3. Okay, y is going to equal 3. Then, okay, so then now we got to figure out what x equals. So what can you do is, there was a step 3, okay, and that is substitute what numerical value, I'll say numerical value, variable equals, into an equation and solve for other variable. Okay, getting messy down here, but hopefully you're listening to me. Hopefully you're hearing me. Okay, substitute what numerical value that variable equals to one of the original equations. I didn't write original in there, but that's what I meant, and solve for the other variable. Okay, so what we're going to do is, now that I know that I have y equals 3, I'm going to plug it into one of the equations. And probably what the easier one is going to be, let's not do this one because this is the one we use to solve to get that y equals 3. Let's do it in the other one here. So let's do this. 2x, this is the original equation here. 2x minus y equals x plus y. Well, what do we know about y? We solve for y. Y is 3. So let's replace that with, okay, let's do that maybe in green. Y equals 3. Okay, so I'll do that maybe in parentheses if we want to make that more simple. I got to put y there. I got to put y over here too, plus 3. And now I'm going to solve for x, right? Solve for x. Subtract x from both sides. That's easy enough. This is just going to become 1x here. If I take that out, right? 1x. And then I got negative -3, and then I got plus 3 over here. So I'm going to add 3 to both sides. And I add 3 to the left side. That makes it 0. Add 3 to the right side. That gives me 6. Okay, so my answer to this one is y equals 3 and x equals 6. Boom, we're good to go, okay? Hopefully that makes a little bit of sense, right? But the more you practice, the more you do something like that, the faster you get at it. So I highly recommend you try to tackle that as much as possible, because then you'll be faster at it. You'll be like, why is it taking so long this time? Well, you gotta go through it. Sometimes you gotta go slowly through some stuff to get faster at it later. Send me an email if you have any questions. Systems problems, right? That's why we do a whole unit in Algebra 1. And yeah, you want to learn to get them. And it's not too late if you feel like you didn't really learn Algebra 1. We can still work on it here. You can still get there. All right, good luck on this. Next up, we have number 28. We'll do number 28 with you momentarily in the next video.